Hello everyone. In this video, we are going to use our Excel and our Excel add-ins in order to help us do confidence interval questions. All right, so let's take a look at this guide. So here we have this scenario where it says oftentimes we don't know what the population mean and standard deviation are, but a lot of times that's exactly what we are kind of looking to approximate. And this is why we do studies and polls to discover some truth about what we don't know. And so let's look at this example with O'Shea. So it says that O'Shea is trying to do a study on the number of hours students at his college spend on their phone each week. He randomly selects 72 students and had them report their number of hours on their phone a week. And the data recorded here. He decides a good place to start is trying to determine the average number of hours spent on their phone each week. And he wants to have a 97.5% confidence interval. Okay, so kind of to get started, let's just figure out we've got a confidence level here. We know our sample size is going to be 72, but let's look at our data. So if we go click on our data button, we can see that we have this big list of time. This is the number of hours that people are spending on their phone per week. So let's go ahead and highlight this. So I'm just going to click it over, and if I just drag to the across, I don't have to scroll all the way down. Kind of speeds it up a little bit. I'm going to copy it, and then I'm going to come into Excel. I'm going to do my paste special, do it as text, and click OK. All right, and here I have my hours on the phone per week. If you notice that this kind of goes over the edge, you can fix that a couple of different ways. I can either double click between A and B. Notice how my cursor changes from a downward arrow to a left-right arrow. If I double click on it, it will make it like this, and then it all fits into a single one. Or another just kind of thing that you can do is if we click on one, if you go to home, I'll pin this down so that we can see all of these. What you can do is you can actually wrap the text. And if we do that, it's this button right here. It says wrap text. And then I can put it in here, show it like that. So kind of handy. Next, what we're going to do is we are going to highlight our data. So I'm going to click on this A1 where I have my label. And then on your keyboard, I'm going to do Control-Shift down, and it will highlight all of the data. From here, I'm going to push Control-M, which is going to pop up my real statistics dialog box. All right, from here, I'm going to say that I'm going to, use my descriptive statistics and normality because I need some pieces of information. I don't know what the sample mean is, and I don't know what the sample standard deviation is. And I need those pieces of information if I want to be able to create a confidence interval. So let's go ahead and click OK on that. And you should get another pop-up window that pops up. That should give you your input range. All right, so I've got my input range here. And what I can do is that's saying this is my data, and I have this first line clicked here where it says column headings are included with the data. So because the first line here is just the title, I want that clicked. Now, if that wasn't there, I would not want this clicked because this is saying that the first one is just a title. If you don't have a title, it will actually take your first piece of data and use it as the title and not use it in your calculation. And your calculations will be a little off. Okay, let's get rid of these two check boxes. And then we got to tell where we want the output range. And I'm just going to say put the output range starting in C2. Doesn't matter where you click, just make sure you're not going to write over anything. And then I'm going to go ahead and click OK. And now I get some good descriptive statistics. So this is my descriptive statistics, hours on the phone per week. I've got my mean, standard deviation, median. Notice how I have an error here as the mode. And this happens a lot of times with continuous random variables because rarely will you have the exact same number pop up a couple of times. And that's what the mode is. Remember, it's the most frequent value. So don't get wigged out if you see an error there. But notice how it gives me my standard deviation. It also gives me my standard error. It already calculates S divided by the square root of N. And we've got our N right here for our count. So you can do some shortcuts, but I'm not going to do any shortcuts right now. I'm going to do this kind of nice and slow. So the first thing that I want to do is, let's start off with the sample size. So I want to know what my sample size is, and I know that my sample size is going to be equal to 72 because I've got it right there. That was my count. So I've got 72. I know that X bar is going to be equal to the mean. So I've got that kind of 20. And I want my sample standard deviation, which is S, which is going to be equal to our standard deviation right here. And I think that's about all that I need from the information from the descriptive statistics. I do need to know what my confidence level is, and back I can get that from my original problem over here as 97.5. So I can do is 0.975, which will then also let me get alpha. And alpha, remember, is just the complement of the confidence level. So I can do 1 minus my confidence level, and I can hit enter. Okay, so I've got those pieces, and then I need to make a decision. Am I going to be doing what type of distribution? And my two options that I have here is I can do a t distribution or I can do a z distribution. Now we use a z distribution if the original problem provides us with the population standard deviation. And in our setup, we have no indication of what we think the population standard deviation is. So because of that, the best thing that we can use is our sample standard deviation, which is right here, what we had the real stats package calculate for us. Okay, so if that's the case, then the distribution that we're going to use is a t distribution. And whenever we use a t distribution, we also need to determine our degrees of freedom. Our degrees of freedom for a one sample confidence interval, just a simple confidence interval like this, is just going to be equal to the sample size minus 1. That'll give us our degrees of freedom. Okay, so at this point, we kind of need to know, are we doing a one-tailed confidence interval? Are we doing a two-tailed confidence interval? And we kind of need to read into this a little bit. So the way that we know if we're doing a one or two tails is if the question gives us some direction. So O'Shea is trying to do a study on the number of students. He wants to do this confidence interval, and he's just trying to determine the average number of hours spent on their phone. He's not trying to say that he's not trying to be like, I'm 70 or 97.5% confident that the true mean is at least some value or no more than some value. Those give us direction and would indicate to us that we needed to do a one-tailed confidence interval. So here, let's put down our tails, and it's going to be 2. We want to do a two-tailed confidence interval. And at this point, let's kind of write out our equation. So the equation that we are going to use is going to be that our confidence interval is going to be equal to x bar plus or minus our t crit times s divided by the square root of n. Okay. So that's our big equation. And remember, we can break this down into two other parts, like two other sub-calculations. So we can first calculate the standard error, and just equation-wise, the standard error equals s divided by the square root of n. Oops, n. There we go. And let's just do that real quick. So if we do that, we can say equals, well, we have s, we can divide by, and we can type SQRT for square root and of n. We can click on this and hit enter. Now, I want you to notice this value right here is equivalent to the standard error that was calculated up here. They already calculated that standard error for you. So in the future, you actually don't even have to calculate the standard error. You can just grab it right here from the descriptive statistics. All right, but that was our standard error. We need to know our t-crit value. And the way that we do this is by using a formula in our Excel. So what we can do is we can do this by writing out this little equation. It's going to start off with the absolute value because we just want to know how far away from the mean we need to be. So we're going to take our absolute value, and then we're going to do t dot inv. It stands for t inverse. Okay, then we need to know our alpha. Let me just do it like this. Alpha divided by 2 since we're doing a two-tailed, and then comma, degrees of freedom. And that will let us know how we can calculate out this t critical value that we need for our calculation. Okay, let's give it a shot. So if we do it, we can do equals ABS, forward parenthesis, t dot inverse, parenthesis. Now we need this probability. We need alpha divided by 2. So I'm just going to go ahead and click up on alpha. I'm going to divide it by 2, comma, highlights that I now need my degrees of freedom here. Click on my degrees of freedom. And then I'm going to do parenthesis, parenthesis for all of that. Okay. And then I'm going to go ahead and hit enter. And it provides me my t critical. Okay. Next little thing that we can do, we can calculate our margin of error. And remember, our margin of error is just whatever we are plussing and minusing from our x bar. So the margin of error is that t crit multiplied by the standard error. Notice how that s divided by the square root of n, that's the standard error. So we can simplify the margin of error to just t crit times the standard error. If we do that, we can do our t crit times our standard error, and we're left with this value for our margin of error. Okay, now we can finish this all up. We can do this by looking at we can say that this is the lower value, this is the upper value. Okay, our lower value is going to be equal to x bar minus the margin of error. It gives us our lower value, and our upper value is going to be equal to x bar plus our margin of error. And there we have our upper and lower. And so we've done everything now. We've done all of these steps. Now there's a couple other questions that we need to answer in this problem. So let's go ahead and go through and do them together. So the first thing is we're going to keep practicing on, can we identify key parts of our problem? So if we look at this first one, it says that the 72 students selected to measure the number of hours per week on the phone for a week. So that is going to be our sample. It's going to be F, because those are the small group that we are interested in. Okay, the list of recorded hours on the phone for the week by each of the 72 students, that is just going to be our data. That's all of our data that we have. So that's letter D. So the mean number of hours on a phone by the 72 students selected, that's our statistic, because it's some truth about the small group that we have. Now, the mean number of hours spent on the phone for the entire college, that's going to be the parameter, because that is what we are trying to estimate. Then all students at O'Shea's College is going to be E, our population. And then the number of hours spent on the phone by a single student is just going to be our variable B. Let's double check and make sure I got that right. FDACEB. Perfect. So that's how we can go through and kind of track through those. Now we have some other questions. Does O'Shea need to worry about the distribution of the individual time spent on the phone? Remember, confidence interval relies on the central limit theorem if we don't know the kind of like original distribution. So let's go ahead and look. It's like, do we need to worry? And the answer is no, because our sample size is sufficiently large to invoke our central limit theorem. And this is true because, remember, we have our cutoff of like the size that our sample needs to be as 30, and we have 72 individuals in our sample. Okay, so next thing says the best point estimate of average time on phone. So our best point estimate of what the population is doing is our sample mean. It's our best single value guess. It's wrong. We know that it's not the true population mean, but it is our best guess from the data that has been provided to us. Okay, then it says like provide the confidence interval for this average phone time, and we had 19.2229 and 21.45. All right, is this confidence one-tailed or two-tailed? This is two-tailed, and we already talked about that because we weren't given any direction on this one. And now we need to just select an appropriate conclusion on this. So it says, okay, we are 95% confident. How do we kind of start these off? Well, typically when we write out our confidence interval statements, we start off by saying that we are 97.5% confident, or whatever your confidence level is. So we are 97.5% confident that the true mean time spent on the phone for students at O'Shea's College is somewhere between those two values. Okay, that looks pretty good. Let's look at over here. We are 97.5% confident that the sample mean. Okay, so the big difference here between our first one and our third one is that we want to make a statement about the true mean. So that's going to be our selection. These other twos, because they're giving a probability to where the true mean or the sample mean is going to be, and the true value is not moving. We're using our confidence interval as a net to try to capture where we think that the true value actually lies. Okay, so now let's kind of move on. It says, suppose O'Shea wanted a confidence interval to claim that the average phone time was at least some value. Okay, so all of a sudden now we're going to start diving into what if we wanted to do a one-tailed confidence interval. Okay, so in order to do a one-tailed confidence interval, we have to change like one thing. We have to change our equation a little bit, and we also need to change how we calculate out our t-critical, and then just a little bit on the lower and the upper. Okay, so let's start off with our equation. Let's copy this. It's going to be very similar if we're going to be doing a one-tailed. So let me start. We'll label this as two-tailed. Two-tailed. Let's label this as one-tailed. And because we wanted to say that suppose O'Shea wanted to claim that the average phone time was at least some value, we're going to do like a lower cutoff. Okay, so we're going to paste in our equation. Oops, maybe not. Let's see if we can't do this again. Copy this. Maybe I'll copy both of these. Copy both of them and bring them up. Okay, the difference here is that for just the lower cutoff, we know that the confidence interval is just going to be minus, and then one of those values is going to be an infinity symbol. Okay, so we've got our lower cutoff because we want to say at least some value. It could go to positive infinity, but we need to know what this lower cutoff is. So we know what x bar is, we know what the standard error is, but we actually have to change our t-crit. So for one sample t-crit, is going to be equal to, same thing as before, my goodness, let's see if I can spell it, absolute value of t dot inverse. But this time we're just going to do alpha divided by 2, or not divided by 2, because we're going to throw all of our error to one side and say degrees of freedom. And that's like the only difference between how we calculate the original t-crit and this t-crit. So let's go ahead and do equals absolute value t dot inverse parenthesis probability. Let's go ahead and click on it. Alpha, comma, degrees of freedom, 2 parentheses, and hit enter. And now we have this new t-critical. Now that I've got this new t-critical, I'm going to do my margin of error. My margin of error is going to be equal to my t-critical times my standard error. I can reuse those ones. Those ones don't change. Like the only thing that changes is instead of doing plus and minus, we're just going to do a minus, and how we calculate out our t-critical. So I've got my margin of error now, and now I'm going to say that my lower is going to be equal to my x bar minus my margin of error. And my margin of error is this entire thing, the t-critical times my standard error, or s divided by the square root of n. And that gives me my lower of 19.3471. And if I click on this, I get my 19.3471 rounded to 4 decimal places. Okay, and this is a one-tailed interval. All right, so that's our lower cutoff. Now, we need to select another appropriate conclusion about this confidence interval. So here I would say that there is a 97.5% chance. Nope, we don't want that. Remember, we still want to be saying confident. Okay. And let's look at this. We are 97.5% confident that the true mean time spent on the phone for students at O'Shea's College is at least 19.35 hours. That's the one that we want. We are confident about the true mean. That is the correct phrasing that we want for this confidence interval. Let's double check. Yep, confident about the true mean. Perfect. Okay, let's do another one. Suppose O'Shea wanted a confidence interval to claim that the average phone time was no more than some value. Okay, so now we are wanting a one-tailed with an upper cutoff. Okay, I'm actually going to, let's see. I'm going to copy a bunch of stuff because it's going to be all quite similar. Paste that. I'm going to copy this. Paste this in here. And the only difference here is that we're going to do plus the t critical times the kind of like that margin of error. Now, the t critical here is the same. No matter if you're going to do an upper or a lower, your t crit is going to be the same. So I'm just going to hit equals and click on that t crit because I've already calculated it. The margin of error is going to be equals to same margin of error, no difference there. The only difference is now I'm going to take this kind of margin of error and only apply it to going above the x bar. So this is not the lower. Let's rename that to be upper. And we're just going to say that that is going to be equal to x bar plus my margin of error. And now I have this, I am 97.5% confident that the true mean is no greater than 21 hours. All right, so this is, we know that the lower is going to be a negative infinity, stretches off to negative infinity, and our cutoff is 21.0207. Again, this is one-tailed, and if we select an appropriate conclusion, we want to say, again, that we are 97.5% confident that the true mean time spent on the phone for students at O'Shea's College is no more than 21.02 hours. So again, the problem with these first two is we're saying chance, and we're not giving any probability to the true mean. The true mean is some value. We're just trying to catch it. And the problem with this one, where it says 97.5% confident, it's that they're confident in the sample mean. I know what the sample mean is. I'm trying to say some statement about where the true mean is. Okay, so there you have it. That's how we go from raw data. So we brought in raw data. We used our tools for it to calculate out all of these descriptive statistics for us. And then using those descriptive statistics, we were able to isolate the variables that we wanted, use our equation for both a two-tailed, a one-tailed with a lower cutoff, and a one-tailed with an upper cutoff, and we were able to calculate and interpret those confidence intervals. Okay, best of luck to you on your own problem.